Another day, another story. In the world of deep learning, understanding the intricate relationships between variables is crucial. Let's explore how these connections are made in the context of neural networks. Imagine you have two variables, error and weight, linked together through a third variable, activation. This connection forms the backbone of deep learning. To comprehend how a change in weight affects error, we start by assessing how a change in activation influences error. This is a fundamental concept in the world of data science. The essence of learning in deep learning is simple. Adjust a model's weights in response to the error it produces. The goal? To minimize that error as much as possible. Now, let's zoom in on one important aspect of deep learning: logistic regression. In a deep neural network with multiple layers, the final layer plays a critical role. It's responsible for classifying data, assigning the most likely label. Each node in the output layer produces binary outputs, 0 or 1, reflecting whether an input deserves a label or not. It's all about making definitive decisions. Inputs. But here's the twist: while the output is binary, the inputs are often continuous. They can vary across a range, depending on the problem at hand. This is where logistic regression comes into play. Despite its name, it's not about regression but classification. It calculates the probability that a set of inputs matches a label. Let's break down the formula. To express continuous inputs as probabilities, we use the magic of mathematics. The exponent of E ensures that our results are always positive. As inputs increase, the probability approaches 100%, signifying high confidence. Conversely, negative correlations lead to lower probabilities. Now, imagine the sum of weighted inputs, the signal passing through a neural network's output layer. This is what logistic regression uses. With logistic regression, we set a decision threshold. Above it, an example is labeled as 1, below it, it's not. You can adjust this threshold to control false positives and negatives. In some circles, neural networks are synonymous with AI. They're like the workhorses of the field, but they don't make assumptions, they learn from data. Yet, AI research is pushing boundaries. Larger networks, like GPT-3, prove the effectiveness of brute force approaches. New algorithms, like capsule networks, require fewer data instances, promising to make deep learning more efficient. While neural networks excel in function approximation, they can be combined with other AI methods for complex tasks, like deep reinforcement learning. DeepMind's victories in video games and Go demonstrate the potential of combining neural networks with reinforcement learning. So, whether it's about understanding intricate connections in data or achieving breakthroughs in AI, the journey continues. Thanks for joining us on this exploration of deep learning and neural networks. This script provides a narrative structure to explain the concepts while incorporating visual cues for better understanding. Thanks for watching.